Okay, hello everyone. I believe that I am audible clearly, and you are also able to see my screen, right?
Yes, sir.
Okay. So let us begin our discussion regarding electrophoresis. And as we did in the last class, I will just revise it a bit for you, and later we can dwell more into understanding the aspects related to the theory of electrophoresis. So today's class will be more related to the theory of electrophoresis. Okay, so as we move ahead from what we did yesterday, uh, we were understanding a bit more about the electrophoresis procedure, basis of the procedure, and in that we actually uh, understood that how electrophoresis is important and how is it different from other separation methods. It's more of what you can say, it's more of a characterization method compared to other methods that you have studied, like chromatography, and another method that you are going to study, which is sedimentation. Both of these methods are more related to isolation and purification, while electrophoresis has to deal with majorly with the characterization of macromolecule. And the molecules which are eventually separated during the process of electrophoresis, on the basis of their migration, you can ascertain something about the molecules' characters. Especially these molecules fall into a category of either proteins or nucleic acids, or you can say their component parts. So essentially electrophoresis, as we saw yesterday, it is just the migration of electrically charged entities under the effect of electric field. But there is another such procedure which actually is similar to electrophoresis, which we can consider as the foundation of electrophoresis, and that is called as electrolysis. Now, electrolysis is a procedure which is mostly associated with electrophoresis, and it is responsible for conduction whatever happens during the electrophoresis procedure. Although the molecule of our interest also carries some degree of charge, but during electrophoresis, the major emphasis is only on its migration towards either of the two electrodes, depending upon its charge status, rather than allowing that molecule to reach to the electrode. Because once any molecule charged entity reaches to the electrode, it undergoes the process of neutralization, or like for water, which is carried along by the charged entities to either of the electrodes, it leads to the process of electrolysis that is responsible for the conduction of current in the external circuitry. So overall, that's what we did yesterday. For conduction of current in the electrolyte solution, majorly the current is carried by buffer ions. The reason why we incorporate buffer ions also, we talked about this in greater detail yesterday, so I will not emphasize more onto that. But the essential fact that you incorporate buffer for conduction of current is to avoid any pH alterations during the electrophoretic procedure, because the biomolecules which are going to gain the charge during electrophoresis is essentially because of the pH conditions. of the medium in which you are going to carry electrophoresis. And hence, when we, instead of using buffer, if we just use an electrolyte, then there could be a problem which might get your molecule change its charge status, and hence will affect its migration. So to avoid it, you actually use buffer during electrophoresis. We talked about the cathode and anode reactions also yesterday, which are responsible for which are responsible for electrolysis of water and leads to generation of hydrogen as well as molecular oxygen. So that is all what we did yesterday. So today we are going to talk more about migration of an ion under the effect of electric field, what governs this migration that we are going to talk about. And we will be discussing what are the controlling elements which will control the migration of ion under the effect of electric field, which is the basis of the electrophoretic procedure. So in case you are having any doubt till now, whatever we have discussed on those points, you can ask me right away, or else I will consider that you have understood this fundamentals of electrophoresis, and we will now move into the theory behind electrophoresis procedure. So is there anybody who has any doubts regarding whatever we have discussed till now? Okay, so I will consider that most of you have a clear understanding of how electrolysis forms the basis of the electrophoretic procedure. So now we move ahead in terms of understanding what are the controlling elements. The force which acts on any charged entity when you put it under the effect of electric field is dependent upon the charge of the molecule. So if we consider a spherical molecule with a charge Q, then the force acting on that molecule under the effect of electric field will depend upon, obviously, the field strength that you're applying. Now, here the field strength actually is given in terms of delta E upon D. What this stands for is delta E is the potential difference that is applied between the two electrodes, and D is the distance between the two electrodes. So if you want to calculate the strength of the field, then you will have to consider this entire quantity altogether. That is delta E upon D. So the field strength is represented like this. We will deal with this in greater detail when we understand the factors that are going to affect the electrophoretic mobility of the molecule. Okay, so any charged particle with a charge value of Q under the effect of electric field, which is denoted by delta E upon D, will feel the force which is equivalent to the product of charge and the field strength. Okay, this much is fine. Okay, so I will consider that this much is fine with you. Now, there is another thing that is happening when any charged molecule is set in motion under the effect of electric field and is moving towards a particular electrode depending upon its charge status, then while it's moving, its movement is not what you can say is a smooth movement. It is actually going to face some degree of resistance while it is moving towards the electrode of opposite charge. Now, this resistance is because of the medium in which the molecule is suspended. So now this, I normally give this analogy when we are discussing this point. It's something like, just imagine that there is, you want to move towards the blackboard in the classroom, and you are standing at the very opposite corner of the blackboard. And if you want to move, you need to pass through a crowd of students who are standing in between. So obviously, when you are moving towards the blackboard, you are going to face resistance due to this crowd of students which are in your path. And that resistance will be obviously opposite to your direction of movement. Same is the thing when a charged molecule is moving under the effect of electric field to oppositely charged electrodes. There are other molecules which are having opposite charges and are trying to move towards the opposite direction. And this molecule which is moving, say for example, the charge on the molecule is positive, it will move towards a negatively charged electrode, that is cathode. When it is moving towards cathode, there are certain negatively charged molecules also which are trying to move towards anode, right? So it needs to pass through this crowd of negatively charged molecules to reach to oppositely charged cathode. Now, when it is doing so, it is going to feel the resistance due to the movement of oppositely charged molecules. Apart from that, there are neutral solvent molecules also. There are buffer ions. So there is a lot of crowd through which a charged molecule has to move. So it is going to feel that resistance, and that resistance, the force of that resistance is given in terms of this quantity, which is represented as 6 pi r eta nu. Now this, I will explain what all these quantities mean. This F stands for the frictional force, okay? And 6 pi r is associated with the volume of the spherical molecule, where r is its radius, okay? So that will decide, this actually is given in terms of what is called as the Stokes equation. And the Stokes equation tells you in terms of the volume of the molecule, and the resistance will be majorly because of the viscosity of the medium in which the molecule is suspended. And viscosity is given by eta, and nu is the velocity of its movement. So now, more the velocity, more will be the friction. So automatically the frictional force is directly proportional to the velocity of movement, as well as it is directly proportional to viscosity of the medium. More viscous the medium, more friction it is going to feel. Obviously, the size of the molecule also decides the frictional force. So, and size of molecule is represented here in terms of the radius of the molecule. So, all in all, this is what is the equation that stands for the frictional force that is experienced by the molecule when it is moving in a solution under the effect of electric field. So now, if we consider a situation where the molecule somehow balances the force of friction that it is feeling and the electrophoretic pull that it is feeling towards the electrode, then we can equate these two forces, what are felt by the molecule, and that is given by this equation. No, before I go any further from here, let me first understand that is this much point clear to everyone? Yes? Okay, so as has been seen in the chat box, I will consider that this much is clear. So now, once we equate these two relations, wherein the charge of the molecule and the field strength is equated with the frictional force, which is felt by the molecule is not going to move further in the electric field. But this equation is actually going to give you a perspective of what will be the velocity of the molecule under the effect of electric field. Now, when we are talking about velocity, we will solve the equation for nu, that is the electrophoretic mobility or the velocity at which the molecule is going to move under the effect of electric field. So that will depend upon all these factors now. So now if we solve it for nu, you get to the relation that delta EQ upon 6 pi r eta d. Now delta E upon d, we know it is the field strength. We can just keep it as a separate entity. So all in all, what it depends upon the mobility of the molecule under the effect of electric field. It will be dependent upon the charge on the molecule, and obviously it is directly proportional to the charge on the molecule, directly proportional to the field strength, is delta E upon d, and is inversely proportional to the size of the molecule, which is given in terms of 6 pi r, and is inversely proportional to the to the viscosity of the medium. So all in all, when we talk about the factors controlling electrophoretic mobility of the molecule under the effect of electric field, the first important factor is the molecule's own charge status. So what's the charge status of the molecule? So it's not only the type of the charge, it also depends upon the density of the charge, how densely charged the molecule is. Okay, so first is the charge of the molecule, and this is the velocity of movement of the molecule under the effect of electric field will be directly proportional to the charge of the molecule. So more the charge, better will be the electrophoretic mobility. Also, it will depend upon the field strength. So better the field strength or more the field strength, better or fast the molecule will move towards the electrodes. Now, we talk about those factors which are inversely affecting the electrophoretic mobility or adversely affecting the electrophoretic mobility. So, electrophoretic mobility will be adversely affected by the size of the molecule. So now, no doubt what's the charge on the molecule. If the size of the molecule is large, then the electrophoretic mobility will be less because it will feel more friction that we have already talked about, because it will have a greater surface area. Okay, so it is inversely proportional to the size of the molecule, and the electrophoretic mobility is also inversely proportional to the viscosity of the medium. So more viscous the medium, more retarded will be the molecule which is moving under the effect of electric field. So any doubts till now? Is this much point clear? Because on this basis, now we are going to discuss how internal as well as external factors are going to play a role during the electrophoretic separation of the molecules. Yes, so if you have any doubts, let me know right away. Till now, is it okay? Yes, so I consider that it is okay. Now, before I go any further, there are a few points that I will have to list over here. First point is that the electrophoretic mobility is directly proportional. Electrophoretic mobility, I will write it in terms of theta, is, nu, is directly proportional to the field strength. So that is delta E upon d. So this entire quantity and the charge of the molecule. What is the charge nature of the molecule? And is inversely proportional. Write it like this. Is inversely proportional to the size of the molecule, which is given by the radius of the molecule, and eta, that is nothing but the viscosity of the medium in which the molecule is suspended. So you need to remember these two factors, because now ultimately, if we talk about certain inherent, what you can say, molecular characters that will decide the electrophoretic mobility, then the inherent factors which affect electrophoretic mobility, the first becomes the charge that we have just seen. that the electrophoretic mobility will be dependent upon the charge. So greater the charge, greater will be the electrophoretic mobility. However, one has to understand this in the context of the pH of the medium, because that is the driver for the charge. I hope that you are getting the point. So if the pH of the medium is not proper, then the charge status of the molecule will not be proper. Now here you need to apply your understanding of pKa that was developed. Okay, so do you remember what was the understanding related to pKa that we developed? Or do you want me to give you a small revision of it? Yes. Concept of pKa is something like this, that if we consider one pKa value, it is in terms of the pH of the medium. So if whenever the pKa is equal to the pH of the medium, then normally the molecule exists in the zwitterionic form. However, when we increase the pH of the medium, then automatically what happens is that the molecule starts to lose its protons and gain a negative charge. So when we draw it in the pH scale, so higher pH value than the pKa of your group will make it gain a negative charge. Okay, while lower pKa value will actually convert the molecule into neutral form, because pKa is normally given in the context of acid. So we consider only loss of proton. So the entity will be charged and gain a negative charge whenever the pH goes beyond the pK. When it is lower than the pK, the acidic group that we are considering is neutralized. Okay, so that is one understanding. Another understanding is in terms of the isoelectric point. It is mostly true in case of proteins. Now, pKa is true in case of nucleic acids because they consist of the phosphate group. Pi is true in case of proteins because they contain both the groups, the acidic as well as the alkaline groups, which are in the acidic and the basic amino acids which are there in the protein. So in case of Pi, when the pH is equal to Pi, the molecule is electrophoretically neutral and it doesn't migrate under the effect of electric field, because here there are equal number of positive and negative charges on the molecule. When the pH is above the Pi value, then the negative charges start to build up and it becomes negative. The molecule preferentially becomes negative. And when the pH is below the Pi value of your protein, then the molecule preferentially gains a positive charge. So that is what is the understanding in terms of pH of the medium. So although this depends upon the molecule's inherent groups that it harbors. Okay, is this much fine? If you are having any doubts, let me know. Yes, Janki wanted to say something. Oh, okay, okay. I'm afraid, Janki, I cannot hear you. Your microphone seems to have some problem. But you can write it in the chat box in case it's fine. Okay. Yes, okay. So Janki says that is clear to her. In case anybody else is having any doubt, I'm ready to answer. Or else we will move to the second point, second inherent molecular character, which decides the electrophoretic mobility of the molecule. Should we go to the next point? Okay. So the next point is, so first, as we have talked about the charge, more the charge, better will be the electrophoretic mobility, and the charge status of the molecule is decided by the pH of the medium. So that is one factor. Another factor that is responsible is the size. We have talked about this as well, and it is inversely proportional to the electrophoretic mobility. So larger the size of the molecule, slower will be its electrophoretic mobility. So smaller molecules with greater charge proportion are going to migrate faster under the effect of electric field, while larger molecules with lesser charge are going to migrate slowly. So it is often said that electrophoretic mobility is decided by the charge to mass ratio, is given by Q by M, where Q is the charge and M is the mass. So it is often said that electrophoretic mobility depends upon charge to mass ratio of the molecule, where the mass, lower the mass, better is the electrophoretic mobility, because mass is a character which you can relate with size. Greater the size, greater is the mass most of the times. So we can consider they are directly related. So smaller the mass and greater the charge, more is the electrophoretic mobility. This much is fine. I hope that I'm making the points pretty clear for your understanding. Okay. So the next thing that is also important, like what was highlighted by Shikha. I don't know whether Shikha is here today. Okay. Shikha is perhaps not there today. Okay. But this was the point that was brought up by Shikha yesterday, and that is about shape. Now, although we haven't talked about in terms of shape of the molecule, we have considered that the molecule will be spherical in shape while deriving the relation that we derived in the that you saw in the last slide. But here, the shape of the molecule has a greater, what you can say, role to play when you're talking about electrophoretic mobility of the molecule. So rounded the molecules, as we all know that rounded structures have lesser surface area. So on the basis of that, compared to elongated or extended molecular structure, you can say, if you compare something which is globular, ball-like, and something which is extended or rod-like, if you allow them to move on a particular platform, then the ball is going to move easily compared to the rod, right? And that is because the rod, although might have the same volume as that of the sphere, but the surface area of the sphere is lesser compared to the surface area of a rod. And why surface area is important? Because it is this surface area that is going to feel the force of friction, which we talked about when we were deriving the relation for electrophoretic mobility. So makes sense that if you have two molecules which are of more or less same mass, which we have just now correlated with the size of the molecule. So if we have two molecules which have same mass, so we consider that they have the same size, but they may have different shapes, right? So one molecule which is globular, ball-like, while the other molecule is extended, rod-like, then the rod-like molecule, although has the same mass and same volume as that of the sphere, but is going to feel more friction, and because of that will migrate much more slowly under the effect of electric field. So are all these points pretty clear in your mind, because they are going to play a major role in understanding other aspects related to electrophoresis when we move ahead in terms of electrophoretic understanding. Yes, is this much pretty clear? Okay, so I believe that This much is pretty clear. Okay. So these three features are important and inherent associated with the molecule. So when you're, so in other words, if I put it like this, will it be fine with you that when I say that a particular molecule has shown me this degree of migration under the effect of electric field compared to some other molecule, then in comparison, can I not predict something about the charge status of the molecule, the size of the molecule, and also to some extent the shape of the molecule? Yes? Yes, so certainly I can predict something about the size, shape, as well as the charge status of the molecule when we are comparing two such molecules migrating under the effect of electric field. Two or more, if we know one of the two molecules, then in comparison to that molecule, we can always predict that what is associated with our molecule of interest. So that is what is the basis of molecular characterization by using electrophoresis. However, when we do this, we also need to be very certain about certain external factors which are going to affect the electrophoretic mobility. And considering those external factors, we need to devise our electrophoretic procedure to get to the desired result that we want to get to. Okay. So what are these external factors? The first and the foremost is the applied electric field strength. Now here, till now, we haven't discussed much, right? Till now, it was a one-way kind of a talk. That means I was explaining you all the essential theoretical details and you were listening. But now I would want you to turn on your microphones and discuss it in greater detail so that I can understand to what extent you have understood the things. Okay. Now, when we say field strength, then there are certain factors that we need to look upon to. The first and the most important factor is the voltage or the potential difference. Now, before I go any further, let me hear it out from you people. What do you understand by voltage or potential difference? We have discussed this briefly when we were discussing spectrometry. But I don't know whether you still remember or you still have the same understanding of potential difference or not. Yes. So can anybody tell me what do you understand by the term potential difference? Yes, anyone? Okay, let me ask. Okay, Sarvesh, can you tell me what is the potential difference according to you? Okay, he has. Janki has given something, difference of electrical potential between 2 points. Okay, it's fairly good, but I want a better explanation. So if anybody can give. Okay, Arya says voltage difference across two ends of the conductor. Arya, can you turn on your mic, please?
Yes, sir.
Okay, so can you just elaborate what you are trying to convey here? What do you mean by voltage difference? What is voltage?
I mean, I actually meant that the conductor has different what we say, like one is a positive and the other is a negative one. So and the voltage is not constant basically. So it changes, like it is different on one end and on the other. I mean, it's not the same. So basically, the difference is known as a potential difference. I mean, according to me.
Okay, fair enough. You were close to what actually potential difference means. But Sarvesh is saying that according to what definition he learned in his 11th standard class, he says that the work needed to bring a charge from one point to another in an electric field is what is potential difference. I'm not very sure whether this definition holds good or not in terms of understanding that what is potential difference. Okay, Tanaya also is actually echoing what Sarvesh has defined potential difference as. No doubt this could be the definition of potential difference, but what do you understand by it? That is more important, right? According to me, you should actually understand what is meant by potential difference. Let me give you a perspective. Maybe that will clear the things in your mind. Okay. Now, if I write it like this, okay. So now imagine that this is, say, one electrode, say cathode, which is at a higher potential, and another electrode is, say, anode, which is at a lower potential. Now, I am talking it in terms of potential of harboring electrons. So, if I'm talking about the capacity of a conductor to bring about reduction reaction, then I can consider cathode as the electrode which is at higher potential of donating electrons. So because it has higher potential of donating electrons, so it is electron rich. Can I say this? Arya?
So can you repeat?
Okay. So if I consider that cathode is at a higher potential, and I describe the potential of cathode as the potential of donating electrons, then whoever is donating something must be having that particular thing at a higher concentration, right? So can I consider that cathode is rich in electrons and hence it has a higher electron donating potential? Yes, okay. So I can consider this, right? In the similar context, the potential of donation of electrons is very low at anode, and hence compared to cathode, it is positive. That means it will be better in accepting electrons than donating electrons. And hence we consider, say, cathode at a higher potential of electron donation compared to anode. It's reverse way also true. Can I say this, that anode is at a higher potential of accepting electrons compared to cathode? Yes, I can also say this, right? So when I am trying to judge that whether what is the difference in the potential of cathode versus anode, then I can take any of the two parameters. Either I can take electron donation potential, or I can take electron acceptance potential. In both the cases, either of the two electrodes will be at a higher potential compared to the other, but the difference will always remain same. Is it fine? So if I consider, okay, so I believe that, okay. So if I consider now, cathode is at a higher potential of donating electrons, and now when we say that there is conduction happening between these two electrodes, now conduction here I am denoting in terms of this ball which is going to move from cathode to anode. Because now why it is going to move from cathode to anode is something like electron moving from cathode to anode, because cathode is electron rich and anode is electron deficient. So the movement will be always from cathode to anode. So consider this situation, that cathode is at a higher potential and anode is at a lower potential, and the two, in between the two, there is movement of an electron. Okay, so if we show it like this, then there will be movement of electron from cathode to anode. Fine. Now, when we are talking about the field strength, it's not only potential difference that matters. Okay. What also matters is the distance between the two electrodes. Now, why will that matter? Can anybody elaborate? If we have this much of understanding clear in our mind. Why will the distance matter? Yes. Imagine that both of them, that is cathode as well as anode, stay at the same potential, what we discussed just right now. Okay, but the distance changes. Is this possible? So you can see that the height of cathode is same, and the anode is also at the same value. So I can denote cathode here and anode here, say for example. Okay, and now I am again allowing the electron to flow from cathode to anode. What has changed according to you? Time. Okay. So now distance we have changed between the two. Yes, Tanaya is quite good at it, in the sense that Tanaya says that speed changes. Speed is actually dependent upon, that is, velocity of movement of the electron between two electrodes is going to depend upon what's the slope, right? When I increase the distance between cathode and anode, keeping their potential difference the same, potential difference is same, but the distance has changed. So automatically the flow with which, or the speed with which the electron was moving between cathode and anode in this situation was faster compared to the speed with which the electron is moving because of increase in the distance between the two. So why this is important is because this is going to be deciding the field strength and what kind of force the charged entity under the effect of these field strength is going to feel, and that will decide the speed or the velocity of the molecule moving under the effective electric field. So we consider both of them together. We don't only consider potential difference. So you might say this, that if I increase the potential difference, the speed will increase, right? But if you increase the potential difference, and if you continue to increase in the same proportion the distance between the two electrodes, then the speed will remain same. Does it make sense? Yes? Should I repeat it for you again? Yeah. If I increase the potential difference, that is the voltage between the two electrodes, but in the same proportion, I also increase the distance between the two electrodes, then the speed of the molecule is going to remain the same. I can put it in other words as well. The potential difference remains the same, but the distance increases, then the speed will drop, because the field strength, that means the difference in the potential, the slope at which the molecule is going to move, just like this example, that slope is going to change, and because slope changes, the speed with which the molecule is going to move across the electric field is going to change. Is this much fine? Yes. Okay. Something here. Okay, fine. Now, when we are moving a molecule or a charged entity between the two electrodes, say from between cathode to anode, what is actually happening? When the electron moves from, say, cathode to anode, you need to re-establish this potential, right? And that re-establishment of the potential is done by the external circuitry, in which the electrons always move from anode to cathode. Now, this we have talked it in terms of field strength in the medium in which the electron bearers are actually ions, because electrons are insoluble in the aqueous system. So the electron bearers here are the conducting ions, which are going to carry the charge from one electrode to the other, most of the times between, say, cathode and anode, the movement. However, when the ions are moving between cathode and anode and carrying the charge, then the speed with which they carry the charge per unit time is referred to what? Is called as? So another parameter comes into play. It's not only voltage that will be the point of consideration here. Another parameter comes into play, and that is what is current. Current is defined as number of charges reaching to two electrodes per unit time. Okay, so as we have reached almost to the understanding that potential difference will be responsible for the speed of the movement of charged entities under a particular situation, and because potential difference will decide the speed of migration of the charge, can you consider that potential difference will decide the amount of current generated? Can I say this? Yes. So essentially now we have arrived at two important situations. One is we have understood that what is potential difference and how it is a driver of electrophoretic mobility. And also we have understood that how potential difference, increment in the potential difference, can lead to increase in current if we keep other conditions constant. Okay. So what I will do here now today is, I believe that this much is fine for you for today, but there are other external factors as well that we need to consider apart from the voltage and the current. And we need to consider current in greater detail because it's not directly always dependent upon potential difference. There are other factors also which are controlling current. And why this understanding is important, because while carrying out electrophoresis, in order to characterize a macromolecule, you will always have to keep in your mind some basic understanding about voltage and current relationship, because that will tell you or give you a better idea about the characters of your molecule. Okay, so that you'll understand slowly, but for time being, is this much fine for everyone? Yes, okay, good. So now a small thing here is if you have learned something good about electrophoresis today, then I would want you to tell me that, because most of you are not turning on your mic today. So if you have actually learned something better about electrophoretic theory or electrophoresis theory, then please post in your thumbs ups over here so that I can understand that you have understood the concepts pretty well. Okay, so if you like the today's discussion, then okay, good. Thank you, Sarvesh. Thank you, Janki. So I believe that you are taking home some good stuff along with you when you are learning the concepts of electrophoresis and the factors affecting electrophoresis. So that's it for today. In case you are having any questions, you can ask me right away, or if there are any queries regarding today's discussion or yesterday's points, then you can ask me right away. I'm here for 2-3 minutes more, or otherwise you can just call it a day. Thank you.